We all know, actually, why we're here. It's to look at what happened, particularly in Run 14, a sodium reactor experiment. Just real quickly on my personal background, I wanted to get you a feeling as to how I got pulled into this. And most of my career, almost all of my career, has been involved with the development of methods to analyze severe accidents, to look at the release of radionuclides in those accidents, and then also to assess the risk to the public from those accidents. At the time of the 3 Mile Island accident, the group that I was involved with was about the only organization, or was really the only organization, that had methods to analyze severe accident behavior in light water reactors. So we helped the NRC, we're an NRC contractor at that time, and then we also helped them in the review of the accident following that. In 1999, the work that I did early in my career was at a research organization called Battelle Memorial Institute. In 1999, I became a professor at Ohio State University, which is just down the road from Battelle, and there I teach and I also do research. Over the last couple of years, we've been working on a project with the Department of Energy to look at realistic assessments of radionuclide release in severe accidents in sodium-cooled fast reactors. And although there are some significant differences with that versus the SRE, the fuel behavior is very similar. So a couple of months ago when I got the call from Sandia and they said, would you like to participate in a review? I went back and I had the book, actually the Thompson book that Tom made the quote out of, that had the review of the SRE accident in it. And from looking at that, I knew it was going to be interesting, and so I was curious, and I said, and I also recognized it might help me in my project that I was doing with the Department of Energy. I said, yeah, I'll participate in the review. Of course, at that time, I didn't know a lot that I know now about what kind of the background for all this was. I didn't know that there were the estimates for very large releases of iodine and cesium by Lochbaum and Dr. Vieira. And I also didn't know about the concerns that had been raised locally about public health concerns and this type of thing. So I didn't really know exactly what I was walking into when I agreed to do this. Okay, so now from my technical review, and you'll see why as we get into it further, I really don't think that the conclusions that Lochbaum and Vieira drew about the possibilities of as much as 30% of the iodine and cesium being released in this accident are real, and I'll describe those reasons in a little bit here. And basically what I want to try to do is to try to explain in lay terms what the reasons are that we think that the iodine and cesium really didn't get out and what did get out. Okay, now Paul already mentioned the barriers to the release of radionuclides. We really have to understand that to get a feeling as to what had to happen to give us a release. And Paul mentioned his first barrier was actually the fuel itself, and it is true that the fuel really is a barrier to the release of all of these radionuclides. This particular kind of fuel, if you irradiate it for a substantial period of time, you actually will get some porosity, some vacant holes building up in that fuel, and you'll get some migration out of the fuel during normal operation, and we've seen that in experiments with very similar fuel types in the EBR-2 reactor. But in this particular accident, and with this particular reactor, because of the very low amount of irradiation exposure that this fuel had been to, you really don't expect to see very much release. There are some mechanisms by which directly some fission products can wind up outside of the fuel. So you'll see a little bit of iodine and cesium in that barrier area between the penetration area, in that upper shield between the cover gas area and that reactor building. And so that really wasn't perfect. And I think that once you started to get some serious fuel damage, then you got to see that it wasn't perfect, and you start to see some material coming up through there into the reactor building, but never really a large amount quantitatively as far as the amount of radioactive materials are concerned, but enough that they had to do some patching, or they got some significant levels. Maybe I'll back off and say I'm not going to take advantage of Tom, and let me take advantage of one thing at this point, because we'll just bring it up later, and that is you actually can get some particulate material up into the reactor building as a result of noble gases that transport to that area as noble gases. Then they decay into things that actually do form particulate. And so you can get, so there's no question, there was some particulate material that deposited on surfaces in the reactor building, and there were swipes that were done that measured that, as well as these constant area monitor, these cams, these constant monitors where there's filter paper and deposits on there. So there definitely is some particulate up there. But that wasn't the major element of Tom's arguments anyway. I don't think he was just an item of curiosity. But you really can get noble gases transporting up there, decaying into elements that actually form particulates that are also radioactive. Okay, and then the other thing is the reactor building itself, and in commercial reactors today, we have containments that are robust. They can take a large internal load. Partly they have to do that because in the light water reactors that we talked about before, you have the potential for this high pressure water to depressurize and give you a big pressure load. So you really do have to have a robust containment that's leak tight. But what was used for the sodium reactor experiment was a confinement concept, in which what they do is they establish a negative pressure inside of the containment. So if you have a release to the containment, to this reactor building part, then you have in leakage. Now, in order to do that, you have to evacuate gases out of the top. Now, a large fraction of the reactors that were built at the time of the sodium reactor experiment were of this confinement type. They used confinement types rather than containments. I'm not a fan of confinement types. There are lots of people even today that are talking about with future reactor designs using confinement systems rather than containments. There are other elements of the confinement system concept that we use at sodium reactor experiment that I'm not a big fan of either. But I do think that probably in this accident, that system worked adequately as far as the protection of the public. It did require some controlled releases of noble gases as a minimum. Okay, now let's get to the heart of this, which is the release of radionuclides from overheated and molten fuel. Again, Paul talked about the noble gases which react with almost nothing, the xenons and the kryptons. And part of the reasons why the exposures aren't too big from xenons and kryptons is that if they're released, there's just an external shine on people that gives them a dose, whereas one of the reasons we worry about things like iodine and cesium is that you could breathe them in, or you could ingest them if they fall on stuff, and you can get an internal dose as a result of that. So typically, the kinds of exposures that you could get from them are potentially higher than the xenon and krypton. So a lot of concern now about the radioactive iodine and this formation of a liquid that gives the radionuclides the opportunity to really migrate out of the liquid and potentially get airborne. And there's no question that once that material became liquid, you'd get a significant release of the noble gases that are in there. Virtually all of the noble gases that are in that part of the uranium that's mixed with the iron from the cladding would be released. They get into the sodium, and they also will be released from the sodium to the cover gas. And then the questions are, did they really get pumped to these holding tanks, or was there some period when they were being bypassed to the stack? But again, the question isn't really so much the noble gases as it is the iodine and cesium and what happened to those. And in contrast to the noble gases, based upon our analysis, and I'll explain this, and common understanding of the behavior of metal fuels today, there would be very little iodine and cesium released. So again, iodine has a low boiling point. When the fuel melts, if the iodine were in the fuel as elemental iodine, you expect some of it to be released to the vapor. I'm sorry, some of it's released from the uranium. But I'm going to talk a little bit more about a dilution effect. That is another effect that hasn't actually been discussed today. I'll discuss it in terms of cesium because it's more important with regards to understanding cesium than it is with iodine. Because with iodine, the answer is just a matter of chemistry. And that is the iodine isn't there in the form of elemental iodine. It's in there in the form of iodides. There may be a little bit of cesium iodide in there, but in reality, when these fission products are born, they see a lot more uranium than they see cesium. So the first thing that they see that they want to attach up to is uranium. And so that's what they form, is a uranium iodide. And we know that based upon the measurements, and again, I want to try to keep this at a lay discussion to the extent that I can, but based upon just our understanding of chemistry and what it is that makes different chemicals react in different proportions, there's definitely a strong preference for iodine to be in the form of uranium iodide rather than as elemental iodine. So uranium iodide has a very high boiling point. We just do not expect uranium iodide to be released. So to me, there's no mystery as to why only a small amount of the iodine got out of that portion that was liquefied. Now, why is it that people have worried so much about iodine? Well, one of the reasons is that there was an accident that occurred in England at Windscale with a reactor. It was actually a plutonium production reactor, but had uranium fuel in which there was a significant iodine release. And the question is, well, why was that iodine released at Windscale, and why do I say it wasn't released here? And the reason is that at Windscale, the graphite that was there was on fire, basically. There was air flowing through that facility. The uranium was oxidized by that air, and it changed the chemistry so that the iodine was released as I2. And we understand why it was that there was that release that occurred at Windscale. The other thing that I think has led to some confusion, and I think it's the thing that really led Lockbaum to make these kind of upper estimates that he made, was that when we look at the oxide fuels that we use in commercial light water reactors, and we have developed predictive tools to determine how much would be released. If you look at the kind of accident that occurred at 3 Mile Island, in which you have water boiling off and uncovering uranium dioxide, the melting of uranium dioxide, and actually there's an effect here that's not similar to what happens with the eutectic formation in these metal fuels, in which there's some zirconium that reduces the melting point of the mixture. So we start off with a melting that is much higher than the kinds of temperatures we're talking about, but not all the way up at the melting point of uranium dioxide, which is at about 5,000 degrees Fahrenheit, but at a temperature that's much higher than experienced here. And when you look at the releases, the rates of release of these materials, they are very sensitive to temperature, so that even a small change in temperature can have a huge effect on the volatility, the amount that gets released. So, but the other thing is the chemistry is just entirely different. So basically, when we look at the analysis of uranium oxide fuel melting in a light water reactor, we estimate that there would be nearly 100% release of iodine and cesium from that portion that's molten. And Dave Lochbaum is very familiar with light water reactors, and that's really why he said, well, there's a third of the fuel that's damaged, potentially molten. That's why, as an upper estimate, I would say that there could be 30% of the iodine and cesium released. And he was wrong because his chemistry was wrong. Okay, now let's talk about cesium. And with regards to cesium, cesium doesn't really react with uranium, but we do understand what happens when you take a substance and you dissolve it in another substance, when you have a solvent and you have a small contaminant of that. And if you think of the uranium as it's melting as being the solvent, and you think of cesium as being a small contaminant, and you look at, if I had a block of cesium and I heated it up to its boiling point, you get a rapid release of cesium from that block. But if you take that cesium and you dilute it in a solvent, then the rate of release that you get is suppressed dramatically, and it's suppressed according to the fraction of the contaminant that you have to the solvent material. So because there are 10,000 times as many uranium atoms as cesium atoms within that fuel, you'd expect to see a much reduced release rate of cesium from that fuel relative to if you had had a block of cesium that was standing and you put it at the same temperature. Now there's another thing that also is important, and that is that uranium is a terrific solvent. What I talked about is basically what happens in what we call an ideal solution. But some things are good solvents and some things aren't. Uranium is a terrific solvent. And so the rate of release from uranium is a factor of 100 greater, a factor of 100 less than if it was an ideal solution. So the other factor that says we're going to get a very small release rate of cesium from the uranium is this other factor that of uranium being a great solvent. So for those two reasons, we expect to see a very small amount of cesium get released in the form of elemental cesium from the fuel. But once it does get released, the story's not really over because it has to face the sodium. So basically, what then really happens with sodium, and we know how much iodine and cesium there really were in the sodium, and once the radionuclides get released from the fuel, then if the noble gases, they're just going to bubble up through the sodium and be released. They have very little solubility in the sodium. Any iodine that's released to the sodium pool is going to react to form sodium iodide. And I'll talk about this question. Well, could some of the iodine have been in bubbles that went up with the krypton and xenon? And the answer is yes, but it also depends upon and it's difficult not to get a little bit technical here in terms, it has to do with the pressure, the partial pressure of cesium and iodine that are in those bubbles. And what happens as they move up through that pool is that they will diffuse basically out of the bubble. And the question is, how much of it diffuses out by the time it makes that transit up there? And we have methods to analyze that, and I haven't done the analysis in this particular case where you actually have flow going on that's decreasing the amount of time that you have before those bubbles get to the surface and they release. But that is a mechanism by which if you had some iodine, as I've said before, we have no reason to believe there's any significant release of iodine from the uranium or cesium. But if you did, you can have some that transport up that way rather than being captured in the sodium. Once they're in the sodium, though, then any iodine that's there reacts to form sodium iodide, and it's not going to be released. And any cesium, you've got this same effect that I talked about before, where you've got this very low concentration of cesium within the sodium, and although sodium isn't as good of a solvent, you have a much much larger number of sodium atoms to cesium atoms than we really had in the fuel of uranium atoms to cesium atoms. So that very much suppresses any release that you have of cesium from the pool. And basically what happened to the cesium then, there was a lot of oxygen in that sodium, and I think it could have wound up on surfaces. That's what normally would be happen. It would react with surfaces. But it also, it could have reacted with the carbonaceous material that was in there, or with the oxygen. I think primarily it reacted with the oxygen to form sodium oxide, cesium oxide, and that then it was caught in a cold trap, which is a little bypass region in this reactor where they cool things off and they can remove things that will freeze out. So basically, that's what happened to the cesium. Okay, and I am sorry I already ran through that slide. Okay, so based upon a technical evaluation, and the reality is this is all chemistry, and it's not a question of whether there's a meaningful non-scientific answer or a meaningful scientific answer. Whatever the scientific answer is, it's the correct one. The question is do I have the chemistry right, or don't I have the chemistry right, and what are the things there? But there's speculation of that there could be cesium and iodine released from the uranium, but there's really no technical basis that's been provided as to why you would expect that to be the case. So on technical grounds, I think there's really no reason to believe the conjecture that there would be iodine or cesium released in any significant amounts from this material that got molten. Now, but let's look at the converse and say, okay, there are these conjectures of the release of iodine and cesium. How much evidence is there physically at the plant, the measurements that were taken, that says, I can definitively say that there wasn't a release? And I can't do that. And for the reasons that Tom talked about, when you get into looking at all, well, first of all, you know, if you have a controlled experiment, you can decide just what you're going to measure, and you can make definitive statements. Whenever you look at these accidents, and this accident isn't a lot different from most other accidents, the 3 Mile Island accident, we were actually pretty lucky on the amount of material that was really available that was measured to interpret it. But if you look at the data here, the dilemmas that Tom talked about of looking at these various inconsistencies between things, the lack of data that you really would want, and what you really want are samples where people went in at the right time, they looked at what was airborne, and they measured how much iodine and cesium was there, and that just never happened. Now, there's no data that says there was a release of iodine and cesium. There's no path of cesium downwind where it rained out, and today we would be able to measure it, and we don't see it there. But you can make an argument that says, well, it would, just because of the configuration of this environment here, it could have been farther down, and we've just never looked at the right place to see the cesium. Today, if we went and looked for the iodine, we wouldn't see it anymore. And there was a grab sample that was actually measured in September, and there are arguments, well, if there had been iodine, we would have seen it there. Well, you can argue all sorts of things about, well, when did the release really occur? And Paul talked about the period when he thinks the melting of material occurred based upon those dates, and it was pretty late there. And my own feeling is very much like Tom's, is that I think there had to be this melting had to occur really early, or we wouldn't see in that period where the decay tanks were off scale right around shortly after that period. I'm forgetting the date right now. So anyway, as far as any definitive statements that say, I can't really disprove those conjectures, or rather, I can't really disprove those conjectures based upon the measurements, and I suspect that we never will be able to. The people that really could have answered the question just aren't around, or like me, their memory isn't that good and they wouldn't be able to tell us anyway. Okay, now, one other thing. I want to talk a little bit about projected health effects because I think that one of the things that Dr. Bea in his report talks about are potentially large numbers of latent cancer fatalities in the population, and he estimates something on the order of potentially 250 for these large releases. It all is tied to these large releases of iodine and cesium. And the way that analysis was done is very controversial. And it relates to something we call the linear no threshold approximation, in which we can use some conversion factors that are based upon data that was involved people that received very large radiation doses and extrapolate that to doses that are just a small fraction or equivalent to our normal background radiation. And I'm not going to get into the debate there. There are strong arguments on both sides as to the value of using these data, whether they're very conservative or whether they're not conservative. It is certainly true, however, though, that in that analysis, it's not a matter in Dr. Bea's calculations that there were people in the neighborhood of the plant that received significant doses and they had a fairly significantly high potential to get cancer, and that's what this constitutes this 250 people. It really comes from extremely small doses in his analysis to very large populations of people. And so among this 8 million people exposed, people with very small doses, that's where you really get these fairly large potential numbers of latent cancer fatalities. Well, when I looked at the releases that Lochbaum was talking about with 30% of cesium and iodine, and from my experience with commercial reactors, I realized even though I don't think that those are real, they really aren't that dramatically large releases. And so I did a calculation with a dispersion model using the 30% release of cesium and iodine and fairly realistic meteorology, but very conservative with regards to it. It assumes that all of these releases occur basically instantaneously, that the person that's exposed, this maximally exposed individual that's breathing this in and receiving a dose from the passing cloud, that the wind doesn't shift during this time period. And in reality, these releases that are the controlled releases occurred over a period of 2 months. And the releases, and if there were releases that were being bypassed somehow during the time period of the accident, they were over a period of time when the wind could have shifted, when the guy could have gone off to work, this maximally exposed individual could have gone inside his house rather than standing out there breathing it all in. Anyway, and I calculate a value less than 5 rem for that maximally exposed individual. Well, what does that mean? Well, at 5 rem, using the conversion factors that Bea used, you would estimate that the additional risk of cancer is 3 parts out of 1,000. That is, your cancer risk would, as a result of that event, if you got 5 rem, would be 3 parts out of 1,000, and then that would add on to whatever your background risk is, which is on the order of 25%, something like that. Those same numbers, that also means that your increase would be about 1%. That is, your increase would be increased by about that much. So that's the worst condition that I can think of as far as people that were in the vicinity of the plant. And I don't believe that. And I think that even that number is extremely conservative relative if you started to get into the games of, well, what was the wind doing and how was it shifting and people moving around and stuff like that, versus the fact that I think that Dr. Cochran's numbers, his maximum bounds wouldn't be close to 30%. They would be bounded by smaller numbers than that. So I, in this sense, I fully agree. I mean, now, this doesn't relate to anything else that happened at the site. I didn't look at anything else that happened at this site, either radiologically or chemically. But as far as this particular event here is concerned, even if you believe the Lockbaum's numbers, and even if you believe the use of these conversion factors that Dr. Beye used, I think that you conclude that to the people in the vicinity of this plant, this one event was not a significant event as far as affecting the probability of cancer. Thank you.